So we're happy to have Soffia Arnadottir from University of Waterloo, and she will talk about quantum walks on Cayley graphs.
Okay, thank you for the introduction, and thank you for organizing this conference. I'm very excited to be here. So I will be telling you about quantum walks on Cayley graphs. And the first thing I have to say about this is that if you're scared of the word quantum, then that's very understandable, but you don't have to be. This is a math talk. It does not, you do not have to know anything about any physics or even what the word quantum means. It's fine. So here's my completely useless outline for this very short talk. I will start by telling you about quantum walks, telling you what they are and sort of what we, some behaviors that we look for in quantum walks. And then I will talk about Cayley graphs. I'll tell you what those are. And then I'm going to end with a theorem, stating and proving a theorem about quantum walks on Cayley graphs. And what I want to do with this talk is to show you why studying quantum walks on Cayley graphs specifically is just fun and cute. So let's just start with a quick example. This is a graph. It's a complete graph on two vertices. Sometimes we call it K2, and it has two vertices, U and V, and they are adjacent. There's an edge between them, and I'm going to use this example to define the adjacency matrix of a graph. And so the adjacency matrix of this graph is this matrix here, 0, 1, 1, 0. It is indexed by the vertices of the graph, and then in the UV entry and the VU entry, we have ones because the vertices U and V are adjacent. But on the diagonal, we have zeros because U is not adjacent to itself and V is not adjacent to itself. So that's the adjacency matrix of a graph. It's indexed by the vertices, and then we have ones wherever the vertices are adjacent and zeros everywhere else. Okay. So let's define a quantum walk. We take an adjacency matrix of a graph and call it A. And then the continuous time quantum walk on the graph is given by this matrix U of t, defined as e to the power of ITA, where t is some real number. We can think of it as time. And then this matrix U of t is called the transition matrix of the walk. And if people are familiar with random walks, then you might notice continuous time random walks. You might notice that this is the definition is quite similar to that. For a random walk, we would get the matrix e to the power of I times minus t times some matrix. And so it's just the I that is different here. And in the case of a random walk, we get a stochastic matrix where the entries are probabilities. And the way we can think of this is that we have a walker who starts walking at a vertex U, and then she walks around the graph, and then at time t, we want to know what's the probability of her being at a specific vertex. And this is going to be the UV entry of the matrix. In this case, we don't get stochastic matrices, we get unitary matrices, and their entries are not probabilities, they are amplitudes. But we can think of it in sort of a similar way. And the motivation for studying quantum walks, it comes from physics. And if you want to know more about that, you can look at these two papers by Bose from Sugata Bose from 2003 and Matthias Christant and others from 2005. I'm not going to go into any physics here, but that's sort of where the motivation for quantum walks comes from. And so we're going to look at our very simple example again of K2. Remember that this is the adjacency matrix, and when we take powers of this matrix, the even powers are just going to be the identity, and the odd powers are just going to be A again. And so if we calculate the transition matrix, we get that e to the power of ita is this infinite sum, and we can collect the I terms and the A terms, and we pick out these two familiar Taylor series. So what we get is the cosine of t times the identity matrix plus I sine of t times A. And so so what we want to sort of look at is what sort of behaviors do we see in these walks. And a particular one that we are interested in is called perfect state transfer. So perfect state transfer between distinct vertices u and v in a graph occurs when the u column of the transition matrix is equal to the standard basis vector indexed by v times some scalar, which is going to have absolute value 1. And we can interpret this as we started our walk at vertex u, and then at time t, we know that we are at vertex v with probability 1, or amplitude 1, if we want to. Yeah. And this is sort of a strange behavior. Again, if you're familiar with random walks, this is something that does not happen in random walks. And it's quite rare as well. It does happen in some graphs, but it's rare. And so we are interested in finding graphs where this happens. And so this is when u and v are distinct vertices. We call it perfect state transfer. Sometimes we abbreviate it to PST. I might use that as well in this talk. But if a similar thing happens where we start at a vertex u and we return back to vertex u at some time t with probability 1, then we call u. We say that u is a periodic vertex at time t, and if this happens at every vertex in the graph at the same time, then our transition matrix is going to be a diagonal matrix. And in this case, we say that the graph is periodic. So once more, we're going to look at our K2 example. We already calculated this transition matrix. And now if we just pick some specific times, we take t to be some specific values, we see that when t is pi on 2, we get this matrix here, 0i, i0, where the columns are standard basis vectors times I. And this is telling us that we have PST from u to v and from v to u at this time pi on 2. And then if we take t to be pi, then we get negative the identity matrix, which means that both vertices u and v are periodic, which means that the graph is periodic. So two things that we notice here is that in this first matrix we have PST from vertex u to vertex V, and also from vertex V to vertex U. So is that a coincidence that happens? And then we double this time of PST, and then we get periodicity. Again, is that a coincidence? And the answer is no. So if there is PST from U to V at time t, then there's also PST from V to U at time t. And this just follows from the symmetry of the matrix U of t. I should maybe have said that we are only considering simple graphs. They're unweighted, they don't have loops. They're all always symmetric. And so the transition matrices are gonna be symmetric. And then in this case, we also can see that if we double the time, then we get periodicity of both of these vertices. And then we have another theorem that's maybe less trivial, that if there is, so that this is a theorem that we call monogamy of perfect state transfer, that if U and V are two vertices that are involved in perfect state transfer with each other, then at no time either of them can be involved in perfect state transfer with some other vertex. That does never happen. So so this is a monogamous relationship. Okay, so now we're gonna put this aside for a little bit, and we're gonna talk about Cayley graphs. Cayley graphs, they sort of bring in a really nice connection between group theory and graph theory. And so we take a group G and take some subset of this group, and for the purpose of this talk, we're gonna assume that the subset is inverse closed and that it does not contain the identity. And then the Cayley graph of G with respect to the set C has the elements of G as its vertices, and then vertices G and H are adjacent if HG inverse is an element of the set C. And then C is going to be called the connection set of the Cayley graph. And there's a lot of things to say about Cayley graphs, and they sort of the group structure gives us a lot of nice things about the graph. But there is a one particular thing that we're gonna look at right now. So let X be a Cayley graph of a group G. And then we know that every group acts on itself by left multiplication. It also acts on itself by right multiplication, but we are, for our purposes, we're gonna look at the left multiplication. It acts on itself and it acts regularly. And as such, we can think of every element as a permutation of this set, the underlying set of the group, which is also our vertex set. So every element of the group is a permutation on our vertex set of the graph. And so we can write it as a permutation matrix. And this permutation matrix is going to be indexed by the vertices of the graph, much like our adjacency matrix. And actually, when we take, because this action is regular, when we take every element of G and assign to it a permutation matrix, this is an isomorphism. So we mapped our group into a group of permutation matrices. And now here's something that's really nice and useful. Let's take all the elements of our connection set and then look at the permutation matrices corresponding to those elements of the group. We add them all together and we get the adjacency matrix of the graph. this is quite significant, and sort of, it's none of this is hard to prove, but it just seems like a it's quite useful, and so we're going to use this to prove a theorem about cube-like graphs. So a cube-like graph is a Cayley graph. It's a Cayley graph of an elementary abelian 2 group. And just to give you a quick example of a cube-like graph, all the hypercubes, for example, are cube-like graphs. This is the hypercube of dimension 4. They are sort of trivial examples because we take our connection set to just be the standard basis of the Z2 to the n. We look at it as a vector space, but we could choose our connection set to be any subset of the group, and we would get a cube-like graph. And so here's the theorem. Let's take a cube-like graph and define this element C to be just the sum of the elements in the connection set. We're now thinking of this as an additive group, so we can add the elements. We add all the elements of the connection set. We get some element C. If C is not the identity of the group, which we call 0 here, then this graph X has perfect state transfer at time pi on 2. This is quite a significant theorem because, as I mentioned before, perfect state transfer is quite rare, but it shows that most cube-like graphs, or a lot of cube-like graphs, have perfect state transfer. Okay, and the proof is actually quite simple. As I said before, we can write the adjacency matrix as the sum of these permutation matrices that correspond to the elements of the connection set. But they are now living in an elementary abelian 2 group, and so they're all going to have order 2, and they commute with each other. Okay. And so the transition matrix we can write as e to the power of it times this sum of permutation matrices, which is equal to this product here, because the permutation matrices commute. And then each factor in this product, just like in our example of K2, because these matrices PR have order 2, this is going to be equal to cosine of t times I plus I sine of t times PR. So the product can be written like this. And if we now take t to be pi on 2, then the transition matrix just becomes I to the power of k times this product of permutation matrices. And a product of permutation matrices is obviously a permutation matrix. Now, two things can happen. We can have that this is the identity, which happens if and only if the connection set that we started with sums to 0. And that's because we are living in an isomorphic group. Now it's a multiplicative group, and our identity is the identity matrix. So if the connection set sums to the identity, then now the connection set, we take the product, and that's again the identity. But when that does not happen, this is going to be a non-trivial permutation matrix. So its columns are going to be standard basis vectors, which means that we have PST in the graph. And that is all I have to say. Thank you.